Okay, ladies and gentlemen, here we go. I'm going to offer a little bit more formal notes than what we had in class, just because time in class, well, you know how that goes. We can't just really take an hour and a half to kind of show you guys the full story of the notes. We have to give you maybe a skeleton. So if you're still a little confused, still maybe unsure why we asked you the family tree, this whole thing of the properties and definitions, even with like the lesson and homework you had these last couple days, these notes are going to serve to maybe give you a little more exposition and explanation where everything's coming from. So you probably want to pause at some point, catch up with me in terms of like what everything is here. Please note that I'm not going to be writing the questions. Instead, I'm going to expect you to fill in your own. You should have enough familiarity with the material and also this type of note taking where that is not really that big of a deal to ask you to now look at the notes and ask yourself that critical question, like what question are these notes answering? So I'll try to make it really obvious where the notes are kind of stopping and breaking to help you guys out in that. But in the end, remember, if you want to use these, you do have to fill in all the sections, which includes the questions out to the side. Okay. So without further ado, let's jump into some notes that's going to help us understand properties versus definitions and kind of where they all fall together. So there's a couple terms here, and I might add some along the way as we go, but these are the three main ones right now. They're going to help us kind of differentiate the definitions and help us suss out what we're calling these properties. Okay, the first one is adjacent versus consecutive. So these are kind of used interchangeably in this particular context, and what they basically just mean is touching. So I'm going to go ahead and zoom in here. I'm going to give you maybe a little example picture that you can copy down as well. So we're talking about adjacent, you have a better sense of what I mean. Let's go there. Okay. So I'm going to draw what is kind of like the standard quadrilateral. This one's supposed to be a parallelogram, but that doesn't really matter here. When I'm talking about adjacent, we're talking about consecutive. I just mean literally like this guy here teamed up with that guy here. These are adjacent because they touch. And that's all this meant by adjacent or consecutive. Adjacent makes a lot more sense when you're talking about side lengths because they can literally touch. But you can also have consecutive angles. Now, it doesn't really make sense to say adjacent angles in this context because they're not touching. But if I'm talking about consecutive, I'm talking about like this angle and like that angle. We consider these consecutive because they're in a row. And so they're kind of used with the adjacent being really the side length part of it, and the consecutive being like the angle part of it. But in the end, they mean the same thing. It's just like boom, boom in a row. Okay. So moving on, let's talk about at least versus exactly slash only, and that's not really much here to talk about. We'll talk about it more in the notes. But you can see a definition I'm offering is that when you say at least, you have to understand you're being very restrictive. Like I would call at least a restrictive version of that definition, where exactly only I would say is the inclusive part of that this type of definition. Because when I say I'm sorry, Lee. I'm sorry. Let's flip that around. Excuse me. I got twisted. I'm sorry. When I say at least, I am being very inclusive. When I say exactly or only, I'm being very exclusive. So if I say, hey, you can only do that exactly once, I mean that precisely as I said it. You can only do that one time, not twice, not three times. Versus when I say like at least, I'm saying, well, do as many times as you want. As long as you do it once, you're meeting the criteria, but it can happen over and over again. And that will be important when we start talking about some of the definitions that we'll get to. The third one is one that we kind of implied, or I guess we should say implied, but we kind of assumed that you knew. And you guys showed us you did have knowledge of this during the actual lesson. But the idea of a polygon is that it's just any two-dimensional enclosed shape that's made only of straight sides. So certainly, if that's the case, they're differentiated by side length. And so we have some very common polygons that are worth mentioning. So some examples may include, let me get a smaller pen. Okay, a quadrilateral, whose definition literally is a four-sided object. So like any four-sided object qualifies as a quadrilateral. That's not really good, but let me differentiate it all better. There we go. We can also talk about a pentagon. And so something like this qualifies as a pentagon. And maybe I'll just put one more. Let's go hexagon. And that's your classic six-sided figure. And so when you talk about a polygon, just talking about stuff like this, which again, that should not be mind-blowing to you, but just something worth noting. Okay, so let's move on. Let's talk about a guiding principle as we continue this work, as we kind of dive into this work. A guiding principle is something that is going to kind of govern all our kind of thinking and working here. And the guiding principle for this type of work is this. All definitions are malleable. Okay. Now the term malleable basically means that they're changeable. And so no matter what you see here in the next few minutes or what maybe you see in class or the last couple of days, know that those definitions can change. Now, what I do not mean is that it can change to something that is pure fantasy. Like under no circumstances can I look at something like this and call it a square. I'm sorry, let me draw. I can't look at something like this and call it a square. That's not what I mean by malleable. What I mean is we're going to give our best faith, best efforts into coming up with a definition that makes sense for the thing that's in front of us. But what the finer points of detail, or the finer points of definition, can change based on the information that we see. That's my way of warning you that some of the stuff you're about to see is not going to match precisely what you saw in class. Part of the reason is that we have 4 classes trying to come up with the same definition, or at least a definition of the same shape. Mrs. Bax also offers some direct input in terms of like what she thought those shapes were too. I even did as well. And so no one of us has the power to change a definition. All we do have in our power is to offer what we best think we think it is, throw it to the group, and try to convince the group we're right. In the end, 1 or 2 people may walk away thinking a shape has a different definition, and that's perfectly okay. It just means their work is governed by their definitions. Again, I'm going to ask you guys to be malleable in your thinking, meaning that you can entertain a thought that we're offering without having to agree with it. Just keep an open mind. There are reasons for the things that we do. Okay? So let's talk about some of the shapes themselves. I'm going to talk purely definition-wise and offer a nice picture for each one. And then I'm going to try to explain why I'm thinking this for the definition and get you guys to maybe think about what the outcomes are for choosing words a certain way. These are in no particular order, so please note that I'm not trying to give away anything in terms of what a tree might look like. I'm just going through these in the way that makes the most sense for me. Okay, so let's talk about quadrilateral. Okay, so I'm going to offer again a definition, and I'm going to offer a picture of a shape. Please note the shape I'm going to try to mark with all the markings necessary that reflects the definition. And I'll try to talk a little about what the marks mean if you have forgotten. So quadrilateral, we can define, I think everyone pretty much agreed, to call this a 4-sided polygon. Okay, a quadrilateral, as you guys found out, is probably the most general of all the family members of this tree. Literally just any 4 sides, and you got yourself a quadrilateral. Now, one thing I want you to pay attention to is that I'm showing you a very general picture of what this shape is. This is not the only quadrilateral in the world. It simply represents what we call the general quadrilateral. The thing that you should know here is that as long as you meet the definition, you take on the term quadrilateral, which is a natural thing I think you guys saw building over the course of time, is that really when you're looking at a shape, it can be called so many different things. Okay, I don't want to belabor that one too much. Let's move on. Next thing I want to talk about is a trapezoid. Let's get this one out of the way quickly. So as far as the definition of a trapezoid goes, it's interesting that the B-Day classes said a trapezoid is a quadrilateral with with only one set of parallel sides, or exactly one set of parallel sides. Whereas the A-Day classes actually accept trapezoid as being a quadrilateral with at least one set of parallel sides. I'm going to offer to you guys a thought that this should be classified as any quadrilateral with at least one set of parallel sides. Okay, so again, let's draw for you the typical trapezoid. So the one that's probably in your head is one that looks something like this. Where the one set of parallel sides to which we are referring occur as the bases, like base 1 and base 2. So the thing I want you to note is that this phrase is controversial. A lot of, again, half the people in our classes wanted to call this exactly. And so the one thing I want you to kind of process in your head is what happens if I call it at least versus exactly. So if you're on board with saying at least, the thing to note is that means that all squares are trapezoids. Okay, that's not the only statement we can make out of it. I can say, well, also, well, rectangles are trapezoids and so are parallelograms. But this is just an example of what the implications are. Now, if you said exactly, that means no other shape is a trapezoid. Now, before you say, well, no, that's exactly what I want, Mr. Collins. I want the trapezoid to be isolated from all the other shapes. I don't want the other shapes to interact with it. My question to you is why? What makes that so? Why are you making that determination? And I'd also encourage you to think if the only answer you have is because I don't like it, or because some other teacher said I couldn't have it, you need a better reason for that. So think of this kind of like a court of law. If you don't have a reason to restrict it to exactly, my advice would be don't restrict it because you don't have maybe all the information. You don't see all the ways these things might connect together. And so if you're sitting there saying, well, I want exactly right now, you might be missing the bigger picture. And so I would encourage you to accept at least, even if only temporarily, until you see more information. And that information is forthcoming later in the week because we're going to talk a lot about areas and perimeters. And that is definitely going to help settle this argument, I think. Let's talk about another controversial one, maybe the other one that's equally as controversial, and that's kite. Okay, so I'm going to call a kite any quadrilateral. Oops. Okay, any quadrilateral with two sets of adjacent, congruent sides. Okay, so in terms of the picture which we're looking, I'm going to draw for you two very typical kites, both of which hold the definition very, very well. Here is kite 1, and this is kite 2. Try my best here. The second kite is actually pretty tough to draw. Okay, so kite 1 takes on this very traditional shape. Kite 2 is more like a delta V or boomerang. Now in terms of marking here, the important marks are the two sets of adjacent congruent sides, which means there's one set that's touching and congruent. Here's the second set that's touching and congruent. Here's one set. There's the other set. So that if I draw a shape that way, so it's a quadrilateral of these qualities, I do end up with a kite. Now again, there's a controversy. And the controversy is actually a word that's up here. It's a word that isn't here. So I'm going to put an asterisk right here. And so let's talk about this controversy quickly. So if it's read just like it's read, that's the definition I'm offering. It's what I would call the inclusive definition. So any shape with this would be called a kite. There were people, and I don't remember which class it said which, that wanted this to be two sets of unique adjacent congruent sides. Meaning that, again, just like the idea of trapezoid only versus at least, if you say I want unique adjacent congruent sides, you're saying these sets have to be different than these sets. Like they have to be different if you want unique. Now I'm not encouraging you to pick unique. I'm simply outlining that if you pick unique, the two sets have to be different. Okay. In other words, something like, okay, so if you were to say something like that, then all squares are kites would also be likewise true. Okay. So I'm going to ask you again to keep an open mind. I've asked that from the beginning. If you don't have a reason why you're forcing them to be different, I would ask you not to force them until you're sure that they should be. Again, we're going to get into things later in the week in terms of finding areas and perimeters that may help explain this a little bit. But for now, I would ask you again, let's go ahead and accept the general definition. All right. Next, let's explore parallelogram. This is like the crowd favorite. Like you cannot get out of a math class anywhere in the United States any year without talking about my friend, the parallelogram. And so the definition, again, almost everyone settled on, with the exception of maybe 1 hour, and we'll discuss that, is that this is any quadrilateral with two sets of parallel sides. Now, in this note, I'm going to also point out, like, I'm not trying to debate the definition of parallel. I'm simply pointing out, like, it has parallel sides. So in terms of providing a drawing for you guys, your typical parallelogram will look like this. Now, as far as marking goes, remember chevrons indicate parallel lines. So there's one set of parallels. This is two set of parallels. Now, again, I'm going to flip back up here just a second to remind you. This is why this at least versus exactly is actually really important. Because if you said, well, it has at least one set of parallel sides for a trapezoid, that would make all parallelograms trapezoids. And again, try to put the personal feelings aside. Is that or is that not okay, mathematically speaking? Is there a reason why you want to include or exclude trapezoid from being related to parallelogram? Okay, now there's no controversy in the definition here except for a very, very small one. And again, I'm just going to pose as a question down here, can parallelograms have more than one side? I'm sorry, more than four sides. Okay. Now the reason I'm posing this as a question rather than a statement is because honestly, like it's still up for debate. Like it's a discussion. It's an open one in the math community. Can parallelograms describe something like, I don't know, a hexagon? Can it describe an octagon? And I'll help you try to answer this question as we talk about the properties in the second part of this video. But for right now, let's just keep it posed as a question and continue on. Okay. Next shape we're going to talk about is a rhombus. Okay, again, definition here, this one actually is not too disputed whatsoever. So a rhombus can be described as any quadrilateral with all congruent sides. And so a little reminder of what that symbol means. It means congruent. It's like an equal sign with a squiggly on top of it. So any quadrilateral with all congruent sides. So a good way to visualize what you're looking at when you're looking at a rhombus is almost like you start with a square, like picture in your head maybe a perfectly square building, and then something comes along and blows it or pushes it over, which makes sense because if it was a square, the only thing different about it is that the angles have changed, of course, because it's been kind of pushed, quote unquote, pushed over. So that's going to create what we call a rhombus. Okay. Also notice that I'm not repeating the definition of parallelogram, or I'm sorry, polygon over and over again. I'm starting with the word quadrilateral. If you notice that quadrilateral was assigned to be a four-sided polygon, and all these are being called quadrilaterals, You can kind of take that as like we're starting with a quadrilateral and then we're adding some unique features to make it special. In this case, 4 equal side lengths. Rectangle should come next. Okay. Talking about a rectangle, we're going to talk about any quadrilateral with 4 right angles. In other words, all congruent. Which is kind of your choice how you want to say that. Like I personally prefer the 4 right angle parts versus the all congruent parts, um, only because it gives me more options later in how I can find it. Like if I pay myself into a corner and saying, well, I have to prove all the angles are congruent, that takes a different type of thinking and maybe mathematical process versus when I say I want to prove 4 things are right angles. Because one, I could definitely do some measuring because 90 degrees is a right angle. Versus if I say they're all congruent, then I might have to write a much lengthier proof. Which is something to consider about when you think about words. Like they actually do carry quite a bit of meaning and quite a bit of power. Anyway, a rectangle, I don't believe it, again, is not one that we have in question. So a rectangle typically looks like this. And the 4 90-degree angles are marked in red. So notice on this one, we're not regulating the sides. Even though the typical picture of a rectangle has like 2 sides bigger than the other 2, it's important to know with the rectangle or with any of these definitions, we're just trying to call the most efficient version of the shape, meaning that I want to use a fewest number of words to force you to draw something that I can accept to be a rectangle. Same is true then if we push on and talk about square. Now, in terms of a square's definition, and there will be a little, again, controversy here in a moment, but I'll accept a square to be any quadrilateral with 4 right angles and all sides congruent. Okay. In terms of a picture of a square, you know what this is going to look like, guys. You've drawn squares your whole life. We want a 4-sided object with 4 congruent side lengths and 4 90-degree angles. Boom, 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 boom. 1, 2, 3, 4. Okay. And it's important to note that like the prefix rect kind of means standing straight up or standing rigid, which is actually why they call that a rectangle, because all the sides are upright and all the angles, are upright and stiff. And so like I know part of the definition someone offered was like a rectangle with. You could do that. Like you can call a square like a rectangle with 4 sides that are congruent or all sides are congruent. But everything else has been related to a quadrilateral, so I'm going to kind of keep it there too. Okay, so those are definitely the definitions we want you to kind of pay attention to and use. I know there's some controversy here that still needs to be worked out. Trust me, it will be. It just needs some more work to kind of make that happen. So the last part of this notes, I'll probably cut away for a moment, are to and from the Cornell note paper, because I don't have a lot of room here, to maybe another diagram. And so the first thing I kind of want you guys to pay attention to when you're looking at this work is why do we go through and define things? Like what's the difference between a definition and a property? And if you're looking at any of these definitions, like the one thing I hope you notice is how, I don't know, concise they are, how precise they are, like how they're written in a very particular way to use the fewest number of words. Unlike me, which I think I just droned on for like half an hour already. But that's the kind of point of a definition. And so when you think kind of about the difference between a definition and a property, the main thing I want you to see is how they're used. Okay, so if we look at definition, versus property. Let's establish again like maybe a guiding principle for us, where if I talk about a definition, I'm talking about And this is something we've talked about before too. Like when you talk about this idea definition, you're explicitly trying to create or differentiate the shape that's in front of you. And so, like if I say, well, I want you to make a square, what I'm really asking you to tell me, I'm sorry, to define a square. What you really I'm asking you to do is tell me what needs to be done. So, like I draw something, it's guaranteed to be a square. Which is why these definitions have to be so carefully chosen. Because if you're not careful on your definition, even though in your head you may intend me to draw a square, if you let me, I can draw whatever I want. Like I liken this type of activity to talking to like a little kid. And so like let's say you have like a younger brother and sister, maybe just like this random kid, or maybe your friend's little brother or sister, and you say, "Hey, I don't want you to touch me." Well, they may stick their finger right in your face, like right next to your eye, but they're not breaking your rule. And so, like, if you're not careful with what you intend, um, then I can do whatever you want, whatever I want to do, as long as I'm following the letter exactly. And so, when you think about these definitions, you got to be so careful and so precise. Otherwise, you're going to allow the creator or the person kind of reading your work to make something you didn't want to happen. Which is why definitions are important. Now, when you talk about properties, we're kind of in a whole different ball game. When you think about the property of a shape, this describes all important features. I guess we can also probably throw in measurement. Okay. Now, what that doesn't mean is like just any old thing that a quadrilateral has. Like just like, hey, I wonder how far it is from here to here. Like that's not what I'm talking about at all. I'm still talking about things that differentiate, but these things are not necessarily unique. They help tell things apart, but they do not distinguish. Okay? Whereas you think about a definition, its exclusive job is to distinguish. Now, since their job is to distinguish, they are often unique. So if I think about like the definition of a trapezoid, whether you said at least or whether you said only, that doesn't actually matter. The point being, what are the shape did you define only through a single set of parallel lines? Because whether you say, well, it's at least one set or only one set, it's still a set. You're just really debating like the next set. So there's no other shape that only needs one to be defined. Okay. So I'm going to end this video here. Obviously, I want you to read through this, make sure you come up with your own questions, and then I want you to write a nice summary. And just like before, if you want some bonus, I want you to post your summary. Okay, as a reply on Edmodo. That's what I'm assuming you kind of get in this video, or at least you're accessing it. So if you want to, again, get um, a bonus points, post it as a reply. Alternatively, if you want to post it as a reply to my YouTube channel, because you might just be linking directly to the YouTube channel, you can post as a reply there. Okay, just do me a favor, you post as a reply um, on YouTube. Don't use your last name, but please put your first name and your block. That way, I can identify who you are on YouTube. But being, of course, a public kind of posting place, don't put your last name. And if your username reveals your last name, as long as your parents are okay with you posting, go ahead and do it, okay? But don't forget about the summary process. It's a 3-step process. Number one, of course, you have to reread notes and then highlight mark important information. Okay. Number two, craft a summary that answers the essential question. Okay, and then revise it and post it. Okay. Now remember, the idea of posting it does two things. One, it lets me read what your thoughts are to make sure you got it. But the other thing it does is helps other people who are having trouble processing their thoughts understand it. Okay, so that's going to be the end of this first video. Sorry it was kind of long. I just kind of got off on a couple tangents there. And then part two, what I want to do in part two is maybe give you a better sense of what the properties are and kind of where they belong in the tree, and can give you a sense why we created that tree in the first place. All right, guys, that's the end of part one. I'll see you guys part two.